Okay, so we have an applied linear algebra practice final exam at the graduate level. So let's begin. I'm going to go through this rather quickly. Some of the intermediate steps are not shown. Okay, so number one, we're going to consider the parameterized system given here. That's x sub 1 plus 2x sub 2 minus x sub 3 plus 3x sub 4 equals 2. 2x sub 1 plus 5x sub 2 minus 3x sub 3 plus 8x sub 4 equals 5. 3x sub 1 plus 8x sub 2 minus 5x sub 3 plus 13x sub 4 equals 7. And x sub 1 plus 3x sub 2 plus alpha x sub 3 plus 4x sub 4 equals beta. Okay, so I'm going to just read through A, B, C, D. Part A, perform the Gaussian elimination, determine all values of alpha and beta for which the system has a unique solution, the system has infinitely many solutions, the system has no solution. For part B, for the values producing infinitely many solutions, determine the complete solution set. Part C, estimate the leading order floating point operation count for solving a dense n by n system using Gaussian elimination and back substitution. And part D, explain why pivoting improves numerical stability. So this is a Gaussian elimination, existence, and computational cost problem. So going through this quickly, if we perform the following operations, we wind up getting 3, 8, negative 5, 13. So the left side of equation 3 equals twice the left side of equation 2 minus the left side of equation 1. However, the right side would have to be 2 times 5 minus 2 equals 8. The third equation has a right side of 7, not 8. So right here. Therefore, the first three equations are already inconsistent. So there is no solution for every alpha and beta. So, unique solution, what we could say never, infinitely many solutions, never, no solution, all, alpha, beta. So for dense Gaussian elimination, the cost approximates 2/3 n cubed, plus back substitution cost approximates n squared. Pivoting improves stability because it avoids dividing by very small pivots, which can magnify round-off errors. Okay, so that's number one. Moving along to number two. So number two, compute the inverse matrix using Gauss-Jordan elimination. Verify your result. Determine whether A can be expressed as a product of elementary matrices, and interpret the inverse geometrically as a linear transformation. Well, Gauss-Jordan elimination and matrix inverse, well, again, intermediary steps, a lot of them aren't shown. The inverse matrix is going to be the following. First row, 3/4, negative 1/2, 1/4. Second row, negative 1/2, 1, negative 1/2. Third row, 1/4, negative 1/2, 3/4. And when we check this A inverse equals I. Since the determinant of A equals 4, 4 doesn't equal 0, A is invertible. Therefore, A can be written as a product of elementary matrices. Geometrically, inverse of A reverses the stretching, shearing, and mixing performed by A. So that's number two. Moving along to number three. Okay, so number three, given matrix A, find the LU factorization of A without pivoting. Construct the elementary matrices corresponding to each elimination step. Express L in terms of these elementary matrices. Use the LU factorization to solve this. AX equals column 1, 4, 2. And discuss conditions under which LU factorization without pivoting fails. Okay, so this is LU factorization in elementary matrices problem. So eliminate below the first part, performing these two operations. That's going to give row 1, 2, 1, 0, 1, 1, 0, negative 2, 7. Then the following operations, U is going to equal 1, 2, 1, 0, 1, 1, 0, 0, 9, respective rows. So the multipliers are M sub 2, 1 equals 2, M sub 2, sub 3, 1 equals 1, M sub 3, 2 equals negative 2. So thus, L equals row 1, 0, 0, row 2, 1, 0, row 1, negative 2, 1, and A equals LU. Solving AX equals 1, 4, 2. First solve LY equals B. We get y sub 1 equals 1. 2y sub 1 plus y sub 2 equals 4, and y sub 2 is equal to 2. Y sub 1 minus 2y sub 2 plus y sub 3 equals 2. So 1 minus 4 plus y sub 3 equals 2. Y sub 3 equals 5. So y is going to equal 1, 2, 5 column. Okay, now solving ux equals y. 9x sub 3 equals 5. So x sub 3 is 5 ninths. X sub 2 plus x sub 3 equals 2. X sub 2 is 13 ninths. X sub 1 plus 2x sub 2 plus x sub 3 is 1. So x sub 1 plus 26 ninths plus 5 ninths is 1. X sub 1 plus 31 ninths is 1. So x sub 1 is negative 22 over 9. So therefore x is this column, negative 22 over 9, 13 over 9, 5 ninths. And to add on to this, LU without pivoting can fail if a pivot is 0 or very small. Okay, that's number 3. Moving along to number 4. Okay, number 4, we're given the following for W. Show that W is a subspace of R4. Find a basis for W. Determine the dimensions of W. Extend your basis to a basis for R4. Okay, and part E, determine whether this V is equal to column 1, 1, 5, negative 1 belongs to W. Okay, so this is a vector spaces, basis, and dimension problem. So we're going to rewrite this as A times column 1, 2, 3, 4 plus B times column 1, negative 1, 2, negative 5. So W equals this span, column 1, 2, 3, 4, 1, negative 1, 2, negative 5. The vectors are not scalar multiples, so they are linearly independent. Therefore, a basis is these two, 1, 2, 3, 4, 1, negative 1, 2, negative 5. And dimension of W equals 2. Check whether V equals 1, 1, 5, negative 1 is in W. So we set up this system. A plus B equals 1, 2A minus 2. 2A minus B equals 1. Solving, we get A is 2/3, B is 1/3. So now we check the third component. 3A plus 2B equals 3 times 2/3 plus 2 times 1/3. 8/3 does not equal 5. So that would be no. V does not belong to W. Okay, moving along to number 4. Let's see. Okay, number 4. Consider A is this matrix here. So A through D, find a basis for the column space, row space, null space, left null space for each of these. Verify the rank nullity theorem. Determine the dimensions of all 4 subspaces. Verify orthogonality relations among the 4 fundamental subspaces. So 4 fundamental subspaces, row reducing gives the following. Pivot columns are 1 and 3. The basis for the columns is going to be that state of A equals the span of column 1, 2, 1, 0, 1, 1. Basis for the row space, that's C of A transpose equals the span 1, 2, 0, 1, 0, 0, 1, 1. Solving for AX equals 0, x sub 1 plus 2x sub 2 plus x sub 4 is 0, x sub 3 plus x sub 4 is 0. We let x sub 2 equal s, x sub 4 equal t. Then x sub 1 equals negative 2s minus t, x sub 3 equals negative t. So x equals s times column negative 2, 1, 0, 0, plus t times column negative 1, 0, negative 1, 1. So n of A equals this span, column negative 2, 1, 0, 0, negative 1, 0, negative 1, 0. Okay, and for the left null space, if we solve for A transpose equals y equals 0, a basis is n of A transpose equals this span, 1, negative 1, 1. Rank is 2, and since A is a 3 by 4, dimension of n of A is 4 minus 2 equals 2, and dimension of n of A transpose is 3 minus 2 equals 1. So the 4 dimensions are dimension of A, dimension C of A equals 2, dimension C of A transpose is 2, dimension of n of A equals 2, and the dimension of n A transpose equals 1. Okay, moving along to number 6. Okay, number 6, suppose the overdetermined system AX approximates B is given by A, column 1, 1, 1, 1, column 0, 1, 2, 3, and B is column 1, 2, 2, 4. Derive the normal equations, compute the least squares solution, compute the orthogonal projection of B onto C of A, compute the residual vector and verify orthogonality, interpret the result as a best fit linear regression problem. Okay, so this is an orthogonal projections and least squares problem. So least squares solution is going to satisfy this. A transpose A x hat equals A transpose B. We compute A transpose A, and that equals 4, 6, 6, 14 rows respectively. A transpose B is column 9, 18. So we get row 4, 6, row 6, 14 times column CM equals 9/18. The equations are 4C plus 6M equals 9, 6C plus 14M equals 18. Solving for these, we get C is 9/10, M is 9/10. So X hat is 9/10, 9/10. The projection is P equals A X hat equals 9/10, 9/5, 27/10, 18/5. So the residual is R equals B minus P. That's just going to be 1/10, 1/5, -7/10, 2/5. Checking for the orthogonality, A transpose R equals row 1, 1, 1, 1, row 0, 1, 2, 3 times column 1/10, 1/5, -7/10, 2/5 equals 0, 0. So R is perpendicular to C of A. The best fit line is going to be Y is 9/10 X plus 9/10. All right. Alrighty, so that's number 6. Moving along to number 7. Okay, so number 7, we're given this matrix here. 1, 1, 1 column, 1, 0, -1 column. We want to apply Gram-Schmidt process to the columns of A. Construct the QR factorization of A. Verify that Q transpose Q is I. Sorry about that. Use QR factorization to solve the least squares problem, and AX approximates this column 2, 1, 0. And explain why QR methods are often preferred numerically over normal equations. So this is an inner products Gram-Schmidt QR factorization problem. So we're going to let A sub 1 equal 1, 1, 1, A sub 2 equal 1, 0, -1. And first that norm, A sub 1 is square root of 3. Q sub 1 equals 1 over root 3, 1, 1, 1. Now compute Q sub 1 transpose A sub 2. It's going to be 1 over root 3 times 1 plus 0 minus 1. Gives you 0. So A sub 2 is already orthogonal to A. So therefore Q equals this. Matrix column 1 over root 3, 1 over square root of 3, 1 over square root of 3. Column 1 over square root of 2, 0, -1 over square root of 2. And R equals root 3, 0, 0, root 3. Okay. And we already have over here, sorry about that if I ignored that previously, this norm A sub 2 equals root 2. So Q sub 2 is 1 over root 2, 1, 0, -1. Now, going back to here, that QR, A is QR. So now we solve A sub X, AX rather, approximates this column 2, 1, 0. And using R X hat, Q transpose B equals, using R X hat, Q transpose B, we're going to compute Q transpose B times Q transpose, rather, B equals root 3, root 2, that column. Some people say vector, I just say like column, whatever you prefer. Here, so we get, and it depends on the context. Square root of 3, 0, 0, root 2, x of 1, x of 2, we get equal to root 3, root 2. And this is x hat equals 1, 1. So our QR is preferred over normal equations because normal equations square the condition number. Kappa A transpose A equals kappa A squared. And that could amplify numerical error in relation to letter E. Okay, so sorry if I'm speaking too quickly, if I mispronounce anything. Number 8, that's number 7. Moving on to number 8. Okay, so we're given U equals 1 over root 2 and then 1 for the respective rows of the matrix. Part A, show that U is unitary, compute determinant of U, find the eigenvalues and eigenvectors of U, explain why unitary matrices preserve vector norms, discuss one application of unitary matrices in signal processing or quantum mechanics. Well, I'm just going to do a condensed version of this. Unitary matrices and applications problem. So a matrix is unitary if U star U equals I. So U star equals 1 over root 2, 1, negative I, 1. Then U star U is 1/2, 1, negative I, 1, and times 1, I, 1. And that's going to equal 1/2 times 2, 0, 0, 2, which is I. So U is unitary. The determinant is, determinant of U is 1/2 quantity 1 minus I squared. I squared equals 1/2 of 1 plus 1 is 1. Determinant of U is 1. Eigenvalues, lambda sub 1, 1 plus I over root 2 equals e to the I pi over 4 with eigenvector 1, 1. And lambda sub 2 equals 1 minus I over square root of 2 equals e to the negative I pi over 4 with eigenvector negative 1, 1. Okay? And unitary matrices preserve norms because this norm here, ux equals ux star times ux, x star, u star, ux equals x star, x equals that norm x squared. Okay, I shouldn't have wrote letter E. Sorry about that. That could be looked up. Lots of applications of unitary matrices in signaling processing and quantum mechanics. Okay. So number 9. Let's see. Given matrix A, we want to compute determinant A. Determine whether A is invertible, compute the volume scaling factor associated with the linear transformation A, explain geometrically why determinants vanish for linearly independent columns, and state and prove one determinant identity. And this is a brief, this is condensed version here. Determinants and applicants problem. Computing the determinant by elimination gives determinant of A is 5. Since the determinant of A is not 0, the matrix is invertible. The volume scaling factor is that magnitude determinant equals 5. If the columns are linearly independent, then the image of the unit cube collapses into a lower dimensional parallel pipette. Its volume is 0, so the determinant must vanish. One determinant identity, so if we take determinant AB, is determinant of A, determinant of B. This follows because the determinant measured sign volume scaling. Applying B scales volume by determinant B, and then applying A scales the result by determinant A. Therefore, the combined transformation scales by determinant A, determinant B. Okay, so that's number 9. Moving along to 10. Okay, so number 10, we're given this A. Matrix, find all eigenvalues and eigenvectors of A, determine whether A is diagonalizable, construct an orthogonal diagonalization of A, determine whether A is positive definite, compute A10 using diagonalization. Okay, so eigenvalues, diagonalization, and symmetric matrices problem here. A could be written as A equals 3i plus j, where j is a 3 by 3 all ones matrix. The vector v sub 1, 1, 1, 1 is an eigenvector of j with eigenvalue 3. Therefore, A could be equal to 3i plus j. Lambda sub 1 is 3 plus 3 equals 6, so lambda sub 1 equals 6 with eigenvector 1, 1, 1. Any vector orthogonal to 1, 1, 1 transpose is killed by J. Therefore, for the two-dimensional subspace, AV equals 3V. Thus, lambda sub 2 equals lambda sub 3 equals 3. Two independent eigenvectors are 1, negative 1, 0 for that column, 1, 0, negative 1 for this column, or any orthogonal basis of the plane x plus y plus z is 0. Because A is symmetric, it is orthogonally diagonalizable. A convenient orthonormal eigenbasis is q sub 1 equals 1 over root 3 times this column 1, 1, 1. Then A equals Q, D, Q transpose, where D equals row 6, 0, 0, row 0, 3, 0, row 0, 0, 3. I should have mentioned we can mention all of this here. This Q sub 1 equals this. This Q sub 2 is 1 over root 2. Negative 1, negative 1, 0 column, and Q sub 3 is 1 over root 6, 1, 1, negative 2 column. Sorry about that. Since all eigenvalues are positive, A is positive definite. Also, A10 is Q, D10, Q transpose, where this D10 equals column 6 to the 10th, 0, 0, 0, 3 to the 10th, 0, 0, 0, 3 to the 10th. Okay, so that's number 10. Number 11. Okay, consider the discrete dynamical system A sub x sub k plus 1 equals A x sub k, and then our A value is this matrix here, rows 0.8, 0.3, rows negative 0.2, 1.1. Okay, A, B, C, D, E. Find the eigenvalues of A, determine the long-term behavior of the system, determine whether the origin is asymptotically stable, compute x sub k explicitly for x naught equals column 1, 0. Discuss how eigenstructure determines the stability of iterative maps. Okay, so this is a dynamical systems interactive iterative maps problem. Sorry. And this is a condensed version. Some steps are glossed over. For A, the characteristic polynomial is determined of A minus lambda I. So that equals 0.8 minus lambda, 1.1 minus lambda, plus 0.06. Lambda squared minus 1.9 lambda plus 0.94 equals 0. Using quadratic equation, we're going to wind up with lambda is 0.95 plus or minus square root of 0.15 over 2i. Or you could write it in this form, 19/20 plus or minus square root of 15 over 20i. The modulus here, modulus of lambda is going to give you, when you substitute these values, it's going to give you square root of 94 over 10. Since the square root of 94 over 10 is less than 1, the eigenvalues lie inside the unit circle. So we could say this, that x sub k approaching 0, the origin is asymptotically stable. The behavior is a decaying spiral because the eigenvalues are complex with modulus less than 1. Okay, so that's number 11. Moving on to number 12. Okay, so number 12, we're given this matrix A. 4, negative 1, 0. First row, negative 1, 4, negative 1. Second row, 0, negative 1, 4. Third row, A, B, C, D, E. Show that A is symmetric, positive, definite. Compute the Cholesky factorization of A. Solve A sub AX equals column 1, 2, 3 using Cholesky factorization. Show that the solution minimizes the quadratic functional f of x equals 1/2 x transpose AX minus B transpose X. And explain why positive definite symbols are important in optimization. So this is a positive definite systems and energy minimization problem. So the matrix A, the A matrix is symmetric. Check leading principal minors, so that delta sub 1 equals 4, which is greater than 0. Delta sub 2, that's going to be 16 minus 1. That's 15. 15 is greater than 0 for that determinant. So that delta 3 equals determinant of A equals 56 is greater than 0. So by Sylvester's criterion, A is symmetric, positive, definite. The Cholesky factorization is A equals L transpose, with L equals the following. For this matrix, 2, 0, 0, first row, negative 1/2 square root of 15 over 2, 0. Second row, third row 0, negative 2 root square root of 15 over 2, and then 2 square root of 210 over 15. Sorry about that. Solving AX, that gives you column 1, 2, 3, gives X equals 13, column 13 over 28, 6 over 7, 27 over 28. The quadratic functional is f of x equals 1f x transpose ax minus b transpose x. Gradient is ax minus b. Setting the gradient equal to 0 gives ax equals b. And since a is a positive definite, f is strictly convex, and therefore the solution is the unique global minimizer. Okay, that's 12. Moving along to 13. Okay, so for 13 here, let A equal this. 3, 0, 4, 0, 0, 5, respectively, those rows. A, B, C, D, E. Compute the singular values of A. Find the orthonormal bases for left and right singular vectors. Construct the full singular value decomposition. A equals U sigma V transpose. Determine the rank and nullity of A from the SVD. And compute the pseudo-inverse A plus. So, here, singular value decomposition. Okay, so we get A equals this 304005. A transpose A is 250025 for those rows. The eigenvalues of A transpose A are 25 and 25. So the singular values are sigma sub 1 is 5, sigma sub 2 is 5. A convenient choice of right singular vectors is V sub 1 is 1, 0 column, V sub 2 is 0, 1 column. Then U sub 1 is A, V sub 1 over 5 equals 1/5, column 3, 4, 0 equals 3/5, 4/5, 0 column, and U sub 2 equals A, V sub 2 over 5, 1/5 times 0, 0, 5 column equals 0, 0, 1. So choose a third orthonormal vector perpendicular to both. U sub 3, negative 4/5, 3/5, 0. Okay, now going over here, U equals this matrix, row 3/5, 0, negative 4/5, 4/5, 0, 3/5, second row, 0, 1, 0 here. Third row, sigma is column 5, 0, 0, 0, 5, 0, and V is column 1, 0, 0, 1. So A equals U sigma V transpose. Since there are two non-zero singular values, rank of A equals 2. Since A has two columns, nullity of A equals 0. And the pseudo-inverse here is 3 25ths, 4 25ths, 0, row 1, 0, 0, 1, 25th, row 2. Okay, moving along to 14. Okay, so 14, suppose a data matrix is given X equals 2, 0, 2, 0, 3, 3, 2, 3, 5, A, B, C, D, E. Explain how the SVD can be used for low rank approximation. Compute the best rank 1 approximation X. Interpret the approximation geometrically. Discuss applications of SVD in image compression, principal component analysis, noise reduction. Explain why singular values measure directional amplification. So this is a condensed version. Applications of the SVD. So the SVD gives X equals U sigma V transpose. The best rank 1 approximation is X sub 1 equals sigma sub 1, U sub 1, V sub 1 transpose, where sigma sub 1 is the largest singular value. Sorry. Computing X transpose X equals this 8, 6, 14, 6, 18, 24, 14, 24, 38 rows respectively. Okay. Doing the computation, again, we skip intermediary steps here. Its eigenvalues are 0, 32 minus 10 root square root of 7, 32 plus 10 square root of 7. So the singular values are sigma sub 1 is square root of 32 plus 10 square root of 7. Sigma sub 2 equals square root of 32 minus 10 square root of 7. And sigma sub 3 equals 0. A right singular vector for the largest singular value is proportional V sub 1 equals that column 3 minus root square root of 7, negative 2 plus square root of 7, 1. Okay. So this, I should have to go back to here. Right singular vector for the largest singular value is proportional to the normalized to the unit length. sorry about that, then u sub 1 equals x sub v sub 1 over sigma sub 1. Okay. All right, so here, best rank 1 approximation is x sub 1 equals sigma sub 1, u sub 1, v sub 1 transpose. Okay, and well, going from here, applications and image compression, keep only the largest singular values. PCA, singular vectors identify principal directions of variance. Noise reduction, small singular values often correspond to noise. Sorry about that. And lastly here, geometrically, this keeps the strongest direction of action of x and discards weaker directions. Singular values measure directional amplification because that a v sub I equals sigma sub I u sub I. So an input vector v sub I is stretched by a factor of sigma sub I. Sorry, that was a bit all over the place. And moving along to the last one, number 15. Okay, so 15. Provide rigorous proofs or definitions for the following. Prove that every real symmetric matrix has real eigenvalues. Prove that eigenvectors corresponding to distinct eigenvalues of a symmetric matrix are orthogonal. Show that orthogonal projections minimize distance. Derive the normal equations from an optimization viewpoint and explain the relationship among rank, determinant, invertibility, eigenvalues, singular values. Okay, so fun problem here, comprehensive theoretical analysis, and this is kind of a condensed version. It could be more expanded. This is more condensed, but so letter A, real symmetric matrices have real eigenvalues. Let A equal A transpose and suppose AV equals lambda V. AV equals lambda V using the complex inner product. V star AV equals lambda V star V. Because A is real symmetric, it is Hermitian, so V star AV is real. Also, V star V is greater than 0. Therefore, we could say that lambda equals V star AV over V star V is real. Thus, lambda is an R. Okay. Part B, eigenvectors of symmetric matrices with distinct eigenvalues are orthogonal. Suppose AU equals lambda U and AV equals UV with lambda not equal to U. Then U transpose AV equals mu U transpose V. But since A equals A transpose, U transpose AV equals parentheses A U transpose V equals lambda U transpose V. So lambda U transpose V equals mu U transpose V. But since A equals A transpose, U transpose AV equals parentheses AU transpose V equals lambda U transpose V. So lambda U transpose V equals mu U transpose V. So quantity lambda minus mu U transpose V equals 0. Because lambda cannot equal mu, thus U transpose V equals 0. And I am going through this rather quickly, so you have this as a reference. Okay. Part C, show that the orthogonal projections minimize distance. So orthogonal projections minimize distance. Let W be a subspace and let B equals P plus R, where P is in W and R is perpendicular to W. For any W, lowercase W in W, B minus W equals quantity P minus W plus R. Since that P minus lowercase w is in W and R is perpendicular to W, we could say that norm here squared B minus W equals that norm P minus W squared plus norm R squared. This is minimized when W equals P. Therefore, the orthogonal projection is the closest vector in capital W to B. Okay, now for part D, deriving the normal equations. Okay, so normal equations from optimization. Least squares minimizes f of x equals that ax minus b norm squared. So expand for f of x equals x transpose ax minus 2b transpose ax plus b transpose b. If we differentiate this del f of x, that equals, differentiate del f of x equals 2a transpose ax minus 2a transpose b. Set it equal to 0, A transpose AX equals A transpose B. Thus, the normal equations are A transpose A, X hat equals A transpose B. And for the last one here, for letter E, we want to explain the relationship among rank, determinant, invertibility, eigenvalues, singular values. So relationship among rank, determinant, invertibility, eigenvalues, and singular values. For an n by n matrix A, the following are equivalent. Rank of A equals n, determinant of A does not equal 0. Inverse A exists. 0 is not an eigenvalue of A. All singular values of A are positive. If A is singular, then at least one column is linearly dependent on the others. Therefore, rank drops, determinant becomes 0. A inverse does not exist. 0 becomes an eigenvalue, and at least one singular value is 0. Okay, so that's all for this practice final exam. Hopefully it helps if you're studying as a supplement, or if you just wanted to do some applied linear algebra problems for practice. I apologize if I mispronounced anything or miscommunicated anything. Thank you very much and have a great day.